Welcome to this rigorous scientific lecture on how blackbody radiation drove the birth of quantum theory. Today we're going to follow the actual workflow that physicists used in the late 1800s to discover one of the most revolutionary ideas in physics. Let's start with the experimental setup. A blackbody is an idealized object that absorbs all electromagnetic radiation that hits it and re-emits radiation based solely on its temperature. In practice, we use a heated cavity with a small hole. The cavity absorbs nearly all incoming radiation, and we measure the spectrum of light coming out of the hole. Step 1 in our workflow is to measure the intensity of radiation as a function of wavelength at multiple temperatures. This was done by experimentalists like Otto Lummer and Ernst Pringsheim in the 1890s. We heat the cavity to different temperatures. Let's say 1000 Kelvin, 1500 Kelvin, and 2000 Kelvin. For each temperature, we use a spectrometer to measure the intensity of emitted light at many different wavelengths, from infrared through visible to ultraviolet. When we plot this data, we get curves that look like humps. Each temperature produces a different curve. A key observation is that as temperature increases, the peak of the curve shifts to shorter wavelengths, and the total intensity increases dramatically. Now here's the question we faced in 1895. What should classical physics predict for these intensity curves? Step 2 is to try fitting classical models to this data. Physicists at the time had two main theoretical approaches. First was Wien's distribution law from 1896. Wilhelm Wien proposed that intensity should follow a specific exponential form. The intensity as a function of wavelength and temperature equals A over lambda to the fifth power times e to the negative b over lambda t, where a and b are constants. Wien derived this using thermodynamic arguments and an analogy to the Maxwell distribution for gas molecules. It worked well at short wavelengths. The second model was a Rayleigh-Jeans law from 1900. Lord Rayleigh and James Jeans used rigorous classical electromagnetic theory. They derived that intensity equals 8 pi k bt over lambda to the fourth power, where kb is Boltzmann's constant. This formula came from counting the number of electromagnetic standing wave modes that can fit in the cavity and applying the equipartition theorem from statistical mechanics. According to the equipartition theorem, each mode of oscillation should have average energy equal to kBt. Step 3 is to locate where each classical model fails. Let's compare these predictions to experimental data. Wien's law works excellently at short wavelengths, the high-frequency region, but it deviates badly at long wavelengths. The Rayleigh-Jeans law works well at long wavelengths, but fails catastrophically at short wavelengths. The failure of the Rayleigh-Jeans law at short wavelengths became known as the ultraviolet catastrophe. As wavelength goes to zero, intensity goes like 1 over lambda to the fourth, which diverges to infinity. This predicts infinite energy at short wavelengths. If you integrate over all wavelengths, the total radiated power would be infinite. This is physically absurd. So here's the critical question. Why does classical physics fail? What assumption in the derivation breaks down? Step 4 is to test whether the failure scales systematically. Let's examine the data more carefully. One key empirical fact discovered by Wien is that the peak wavelength times the temperature is a constant. Lambda max times T equals 2.898 times 10 to the negative 3 meter Kelvin. This is Wien's displacement law. For example, the sun's surface temperature is about 5800 Kelvin. The peak wavelength is about 500 nanometers, which is green light. If we divide 2.898 times 10 to the negative 3 by 5800, we get 500 nanometers. Another systematic scaling is that the total radiated power per unit area goes as temperature to the fourth power. This is the Stefan-Boltzmann law. Power equals sigma t to the fourth, where sigma is the Stefan-Boltzmann constant. Sigma equals 5.67 times 10 to the negative 8 watts per square meter per Kelvin to the fourth. Let's do a back-of-the-envelope calculation. How much power does 1 square meter radiate at 1000 Kelvin? P equals 5.67 times 10 to the negative 8 times 1000 to the fourth, which equals 5.67 times 10 to the fourth watts, or about 57 kilowatts. That's like 50 electric space heaters, all running from just 1 square meter. This shows how powerful thermal radiation is. Step 5 is the revolutionary part, proposing a revised assumption. This is where Max Planck made his breakthrough in December 1900. Planck proposed a radical idea. What if energy is not continuous but comes in discrete packets or quanta? The classical assumption was that electromagnetic oscillators in the cavity walls can have any energy E, continuously variable from 0 to infinity. Planck's new assumption was that energy comes in integer multiples of h nu, where n is an integer, h is a new constant, and nu is the frequency. E equals nh nu, where n equals 0, 1, 2, 3, and so on. The constant h is now called Planck's constant. This means energy levels are like a ladder with discrete steps, not a continuous ramp. You can only have energies at specific rungs. Here's an analogy. It's like money that only comes in 1-cent increments. You can't have a fraction of a cent. Energy became quantized in units of h nu. Now the question is, how does quantization fix the ultraviolet catastrophe? Why does it suppress short wavelength radiation? The answer is that high-frequency modes require large energy packets h nu. At typical temperatures, kBt is much smaller than h nu for ultraviolet frequencies. If h nu is much greater than kBt, the mode is rarely excited because the thermal energy is insufficient to create even one quantum. Step 6 is to fit the new model across all temperatures. Planck derived a new formula using his quantum hypothesis. The Planck distribution is intensity equals 8 pi hc over lambda to the fifth times 1 over e to the hc over lambda kBt minus 1. This formula is remarkable because it combines both Wien's law and the Rayleigh-Jeans law as limiting cases. In the short wavelength limit, when hc over lambda kBt is large, the exponential dominates and we recover Wien's exponential form. When lambda goes to 0, e to the hc over lambda kBt becomes much greater than 1. So intensity approximately equals 8 pi hc over lambda to the fifth times e to the negative hc over lambda kBt. In the long wavelength limit, when hc over lambda kBt is small, we can expand the exponential. When lambda goes to infinity, e to the hc over lambda kBt approximately equals 1 plus hc over lambda kBt. So intensity approximately equals 8 pi hc over lambda to the fifth times lambda kBt over hc, which simplifies to 8 pi kBt over lambda to the fourth. This is exactly the Rayleigh-Jeans formula. Planck fit his formula to the experimental data and determined the value of his constant h. He found h equals 6.626 times 10 to the negative 34 joule seconds. This is Planck's constant. Let's calculate what 1 quantum of visible light energy actually is. For 500 nanometer green light, the frequency is c over lambda, which is 6 times 10 to the 14 hertz. The energy of 1 quantum is h nu equals 6.626 times 10 to the negative 34 times 6 times 10 to the 14, which equals 4 times 10 to the negative 19 joules. In more convenient units, this is about 2.5 electron volts. This is a tiny energy on human scales. Let's compare this to thermal energy at room temperature. At 300 Kelvin, kBt equals 1.38 times 10 to the negative 23 times 300, which equals 4 times 10 to the negative 21 joules, or about 0.025 electron volts. For visible light, h nu is about 100 times larger than kBt at room temperature. This is why quantum effects matter for light. Step 7 is to validate the model by predicting the spectrum at a new temperature that wasn't used in the fit. Let's say we fit the Planck formula using data at 1000, 1500, and 2000 Kelvin. Now we predict what the spectrum should look like at 2500 Kelvin and measure it. When we do this, we find perfect agreement. The Planck formula predicts not just the shape, but the absolute intensity at every wavelength. The agreement extends across the entire spectrum, from infrared wavelengths of tens of micrometers down to ultraviolet wavelengths of hundreds of nanometers. Using Wien's displacement law, at 2500 Kelvin, the peak should be at lambda max equals 2.898 times 10 to the -3 divided by 2500, which is 1.16 micrometers in the near-infrared. Using the Stefan-Boltzmann law, the total power should be sigma times 2500 to the fourth, which is about 2.2 megawatts per square meter. Both of these predictions match experiment to within 1%. This level of agreement was unprecedented. Now let's discuss the profound implications of Planck's discovery. Initially, even Planck himself viewed quantization as merely a mathematical trick to make the equations work. He didn't believe energy was truly quantized. It was Einstein who took the idea seriously in his 1905 paper on the photoelectric effect. Einstein proposed that light itself comes in particle-like quanta, later called photons. The question was, what evidence finally convinced physicists that quantization was not just math but physical reality? The answer is that multiple independent phenomena all showed the same quantization. The photoelectric effect, atomic spectra, specific heats of solids, all required H with the same value. By the 1920s, this led to the full development of quantum mechanics by Heisenberg, Schrödinger, Dirac, and others. From our modern perspective, we can understand why quantization makes physical sense. When you confine waves to a box, like electromagnetic waves in a cavity, only certain wavelengths fit. The allowed wavelengths are quantized by the boundary conditions. If the energy of each mode is proportional to its frequency, and frequencies are discrete, then energies must be discrete as well. Here's an analogy. A guitar string or an organ pipe produces discrete musical notes, not a continuous pitch. The allowed frequencies are determined by the length of the string or pipe. The fundamental constant H sets the scale at which quantum effects become important. It's the conversion factor between frequency and energy. Let me summarize what we've learned about the scientific method in action. Step 1. Careful systematic measurement at multiple conditions, in this case, different temperatures. Step 2. Test existing theoretical models. We found Wien's law and Rayleigh-Jeans law each worked in different regions. Step 3. Locate where and how the models fail systematically. The ultraviolet catastrophe was a clear failure. Step 4. Identify which fundamental assumption might be wrong. Planck questioned the assumption of continuous energy. Step 5. Propose the minimal revision that fixes the problem. Planck quantized energy in units of h nu. Step 6. Derive new predictions and show the revised model fits all available data, not just the failure region. Step 7. Make testable predictions for conditions not yet measured and validate them experimentally. The legacy of blackbody radiation extends far beyond just understanding thermal emission. It revealed the fundamentally granular nature of energy and matter at microscopic scales. It led directly to quantum mechanics, which underlies our modern understanding of chemistry, solid-state physics, nuclear physics, and particle physics. Today, applications include LEDs, lasers, semiconductors, solar cells, and emerging quantum technologies like quantum computing and quantum cryptography. Planck's constant H appears in every single equation in quantum mechanics. It's one of the most fundamental constants in nature. Here's a final thought. Revolutionary science often starts not with grand new ideas, but with careful attention to small anomalies in existing theories. The ultraviolet catastrophe was a puzzle that didn't fit. Planck's genius was recognizing that fixing this small discrepancy required questioning one of the most basic assumptions of classical physics, the continuity of nature-its. Sometimes the smallest cracks in a theory reveal the deepest truths.